So what is the kernel trick about? The main idea is that nonlinear feature transforms might boost our machine learning algorithms, and the kernel trick is a way to do this efficiently. But let's first discuss what the big deal of these nonlinear features is actually about. So if we're working with SVMs are actually linear decision boundaries, but our data might be actually far from linear. So the actual decision boundary might be far from linear. And a general observation is if we are working with high-dimensional data, this tends to be more likely to be linearly separable. Now we can apply a simple trick. We can take our input features and just apply a lot of nonlinear feature transforms first, and therefore we transform our learning problem into a high-dimensional feature space. For example, you could take polynomials and exponential functions and logs and trigonometric functions. And key here is that we really use nonlinear feature transforms, because if we take linear feature transforms, this will yield rotation and sharing and scaling of the features and not really make that more linearly separable. So nonlinear features are key here. So to give you an example, here is some classification problem with two features, x1, x2, and we see that this problem is far from linearly separable. So the negative class is close to the origin and the positive class is around here, and we see no matter how we put the linear classifier, we won't do a good job. But if we take this feature space and transform it into a higher dimensional feature space using this, this nonlinear transformation phi, which essentially just takes x1 squared and x1 times x2 and the cosmetic factor here, and x2 squared. So just taking polynomials of degree 2 and yielding a three-dimensional space where we call the coordinates set1, set2, set3. So we get this space, and we see all of a sudden the problem becomes linearly separable. So we transform the space and apply the support vector machine here, and this would be the solution. And we see we do a perfect job now. So we separate all the positive and the negative examples. So applying this nonlinear feature transform, all of a sudden we can work with a linear classifier. And it's clear if we project back essentially this decision boundary to the original space, we get actually something nonlinear. So essentially taking nonlinear features and then applying a linear classifier yields actually in net a nonlinear classifier, like here. So this is a non-linear decision boundary. So there's a main problem with feature transforms. So we want actually to take many feature transforms, because a priori it's sometimes hard to guess which nonlinear features are the good ones. And we could just start adding greedily features, but this quickly explodes, right? So if we, for example, stick to polynomials up to degree k, and if we have d original features, then this produces d plus k minus 1 choose k features. So for example, if our original feature space is 100 and we take polynomials up to degree 5, so all of them, then we get 75 million features. And this is pretty tough even on hardware nowadays. So just adding greedily features works in principle, but our learning problem becomes also computationally harder and more inefficient. So the key question is, can we do this? Can we work in high-dimensional feature spaces efficiently, so implicitly? And yes, this is the main insight of the kernel trick. So the kernel trick in a nutshell is the following. So many learning algorithms can be formulated as such that they just take the labels and inner products between our feature vectors as input. So the input are our labels and pairwise similarity measures. So these inner products between samples are essentially pairwise similarity measures. And we can collect them, all these inner products and similarity measures, in a matrix K. So in an n times n matrix K, so n is the number of samples. And so the ith row and jth column is just the inner product of sample I and sample j. So note that the inner product is a scalar, regardless of the original dimensionality of x. And now it's clear, if we now had a high-dimensional feature transform phi, so like this 75 million different polynomials, then actually the exactly same algorithm would also work if we provide the same gram matrix. So this K is often called the gram matrix. So if we just replace our features with these feature transforms and then take this inner product, we just get a different gram matrix. So the algorithm doesn't even notice that we take that something changed, that we actually changed the feature space, because in both cases we just provide this gram matrix. So we can replace the features and take different inner products, and the same algorithm just works essentially the same. So it doesn't even notice that we've changed the feature space. But as said, so this phi might be expensive, and computing this inner product in high dimensions might be expensive. So can we do this efficiently? So can we replace feature transform and inner product with a cheap function K? And so again, yes, this is the central idea of the kernel trick. So without explicitly computing our high dimensional features, we might be able to compute this inner product of this high dimensional feature space efficiently. So let's give some definitions. So a kernel is simply a function which takes two feature vectors and returns a real number. So much like inner product, which also just takes two vectors and returns a real number, a kernel is just a function which just takes two training examples and returns a real number. And now a kernel might have a property called positive definiteness, which is defined as follows. So a kernel is positive definite if for any finite collection of vectors, so essentially any finite data set, arbitrary data sets, but finite ones, and any collection of real numbers a1 to an, we have that this inequality holds. So it's this double sum, ai, aj, and the kernel evaluated for ith and jth training example or of these vectors, and this must be larger or equal than 0. So we can write this in vector notation by collecting all the kernel evaluations in a matrix K. So row I and the column J is just the kernel evaluation for ith and jth training example. And this is no coincidence that we again call this K like this gram matrix, because this essentially will turn out to be the gram matrix in this high dimensional space. And so we take this gram matrix, just the kernel evaluations, and an arbitrary vector from Rn, and then positive definite means that this holds. So A transpose times K times A larger equals 0. And again, this must hold for any collection of vectors and any choice of an n-dimensional vector A. So A transpose times K times A larger equals 0 for all possible training vectors and all possible vectors A. So this means if this holds, then the kernel is called positive definite. And now the key result of the kernel trick is the representer theorem, which I won't prove here, but I will just state this theorem, which highlights that there is a tight connection between positive definite kernels and inner products of feature spaces. So it says a kernel function is positive definite if and only if the kernel corresponds to an inner product in some feature space phi. So this means a kernel is positive definite. So this means if you give me a positive definite kernel, I can guarantee you that there is some feature space out there where this kernel just corresponds to the inner product in this feature space. And vice versa, if you give me a feature space, then I can guarantee you that this inner product in the feature space corresponds to a positive definite kernel. So this shows a very tight connection between positive definite kernels and feature spaces. Essentially, this is central to the kernel trick, and so using this in the kernel trick just means we have our feature space, which is expensive, and we can now replace. So the representer theorem allows us to replace this with a positive definite kernel. So essentially, we might, if we have a feature space, we might have a kernel function which actually computes this inner product cheaply, rather than going over the high dimensional feature space and then computing the inner product. We might do this more cheaply with some kernel function. And a crucial insight of the kernel trick is also we don't need to know phi explicitly. So we can actually now start playing with positive definite kernels rather than with feature spaces. So we don't need to know phi. As long as we have a positive definite kernel, we can guarantee that there is some phi, some feature space where we're actually working now implicitly. And the kernel's trick is essentially is a very general trick. It's not only applicable to support vector machines, but also principal component analysis and linear discriminant analysis. And a lot of other learning algorithms can be formulated that they only work with inner products. And whenever you can formulate your learning algorithm that it works only with inner products, you can just plug in the kernel and get essentially a new learning algorithm, a kernelized learning algorithm. And another nice feature of the kernel trick is that it also works with non-vector data now. So, for example, support vector machines and many other algorithms work with input vectors like these xi's here. But what if your data is actually something like strings or graphs or other abstract objects where you don't have a vector space really? So if you manage to define a kernel for a positive definite kernel for these objects, you can actually now use this kernel and embed these objects in a vector space implicitly. This is another nice gimmick of the kernel trick. So here are some kernels. So we have a linear kernel, which is actually just doing nothing. So it's just the inner product of the original features. So this is a valid kernel again, and the corresponding feature function is easy to see to be just the identity. So essentially this linear kernel doesn't do much. We have the polynomial kernel, which is just the inner product plus 1 to the power of p. And it can be shown that the corresponding phi actually computes all polynomials up to degree p. So before we had this example of a 100-dimensional space and degree 5. We computed that this yields 75 million features. Now essentially you get the same effect with a very cheap function. So essentially this is not much more expensive than the original inner product. So this is a tremendous saving in computational power. And also a very widely used kernel is the Gaussian kernel or RBF kernel, which is just the Euclidean distance squared times a bandwidth parameter gamma minus and taking the exponential. So this is like a Gaussian distribution. It looks like a unnormalized Gaussian distribution, and this is called the Gaussian kernel or RBF kernel. And it can be shown that there is no finite feature space corresponding to this kernel, so this corresponds to an infinite feature space, so-called functional space. These are probably the most well-known kernels, but there are tons of other kernels as well. So let's apply now the kernel trick to SVMs. And to this end, here we have again our dual formulation of the support vector machine. And nice, here we have only these inner products of our feature vectors. And in order to kernelize now our support vector machines, we first conceptually replace our feature space x with a transformed feature space phi of x. So we can do this conceptually, and we know that this inner product in our feature space now corresponds to some positive definite kernel k. And this is it. So we start with our inner products xi, xj, and instead we just plug in a positive kernel. And this is it. This is the kernel trick for support vector machines. This is still a quadratic program and convex, and we find a globally optimal solution. So very simple. This is how we kernelize SVMs. But now it's maybe a bit unclear. If we get this global solution lambda star, how do we actually work with this? So how do we classify? So, and in order to see this, recall from slide 47, where we discussed the dual formulation of SVMs, that the solution, the dual solution, so these lambda stars, also give us a solution in the primal W star and also B star. So this is requires some sample xi where the lambda star is larger than 0. So this essentially gives us also the solution in the primal. And conceptually, we still have the same here. So the only thing we need to replace is this x by the feature transformed x. So in principle, we still get the solution W star, which is just this linear combination, but now we work with this feature transformed x, and also for B we have essentially exactly the same formula, but just replacing x with phi x. But so this is, we cannot work with this, or we don't know whether we can work with this, because the whole point of the kernel trick was to not work with this phi. So we don't want these phi's in our solution. So, but you will see in a second that we can get rid of them. And for B, it's rather simple. So we see that we have, for B, we have this W star, and we have this solution for W star. So let's just plug this in here. And we get essentially, so this sum here plugged in here. And we have this phi xi here and yi. And it turns out if we multiply this out, we get essentially phi xj. So we change the running variable here from I to j, because here we have another I. So if we multiply phi xj with phi xi, this gives again an inner product, and we can replace this with the kernel. So for B star, we get this solution. Essentially, we just need to take the optimal solution of lambda, and we have these labels, and we just need to evaluate this kernels here. So we can formulate B again in kernels. And also for W, we can do something, or generally, if we want to classify a new x, so this is a new data point x, which was not in our training set. So we actually don't need W star for this. So to see this, here's our classifier, hx, which is the sign of this affine function here. So this optimal W times our phi of x. So x goes into our feature transformer minus B star. Again, if we take W and plug this in here, we get this sum here. So this sum expressing W times phi x. So this is our new data point we want to classify, minus B. So we saw for B we can express via kernel. So we have already B star. But now again, here we see that when we plug in W, we get this inner product between the phi xi and the phi applied to the new data point. And again, this is just the kernel of our training examples. So kernel evaluated for all our training examples and this new data point. So for classification, we neither need W star nor B star, so the optimal solution in the primal. So we can express the whole classification just with our dual solution, which we got out of this optimization problem. So this is how we classify with kernelized SVMs. So no need to go back to our feature space. No need to compute these primal variables explicitly. So we can express this just with kernels or kernel evaluations. So here are here's some example with some toy data. So the toy data is not linearly separable. So we have this blue class in the center and these red points around. And here we essentially see the fail case for linear SVMs. So when we train support vector machines, so this is from sklearn, we can plug in the linear kernel, and this gives us essentially this decision boundary. So it will somehow fit the linear SVM. So essentially this is the original linear classifier, the support vector machine, and it will do some fit, but essentially it now tells us everything below here is blue. So since most of the points here are, the blue points are on this side, and everything up here is red. So it does a terrible job. And regardless of this trade-off parameter C, so which trades off the weight norm and the slack variables. So a really terrible job. Now we can play with the kernel and essentially just changing this one line, we can plug in the polynomial kernel and up to degree 4. And we see that the decision boundary here is pretty sensible. It depends, of course, on this trade-off parameter. And in particular, this looks like a really sensible job. So essentially, this classifier tells us, well, everything in here is blue, everything out here is red, which really looks like a good solution. And similarly, if we take the Gaussian kernel or RVF kernel, again, we get a sensible solution. So see that with a nonlinear kernel, we get also a nonlinear decision boundary, and this makes a lot of sense. So of course, the kernel is now also a choice which you have to pick for your learning, and you could, for example, also cross-validate it. So to summarize this section, this pretty lengthy section, so we discussed primal SVM and dual SVM, and we already said, well, the size of the primal is number of features essentially, and the size of the dual is number of samples squared. And there might already be, even without kernel, different advantages between these two formulations. So both of them are quadratic programs and convex, and we can find a global optimal solution. Crucially, however, the dual SVM depends only on inner products, and therefore it unlocks the kernel trick for us. And again, the kernel trick in a nutshell is replace inner products with inner products in a feature space and express this cheaply with a kernel function. And the key theorem here is essentially that a kernel corresponds to such inner product in some feature space if and only if K is positive definite. So if evaluations of all the samples, so all these kernel evaluations, if we summarize this in a matrix, then this matrix is positive definite. And we can kernelize SVMs. We can also kernelize other algorithms like PCA, LDA. So we will discuss PCA in this course, but also many other algorithms can be kernelized. And this was, for some time, this was a bit of a sport in machine learning research to find reformulations of classical learning algorithms such that we can just plug in the kernel. Essentially, plugging in the kernel in an old algorithm essentially gives you now a whole library of new algorithms, because you can play now with kernel. So it's pretty modular. As soon as you can reformulate your algorithm to work only with inner products, you can kernelize it and essentially get now a whole library of new algorithms. Kernelized SVMs are pretty strong. So if you have a classification problem, one of your first things you should try is kernelized SVMs and random forests. So kernelized SVMs are pretty strong. And essentially, so in the 90s and 2000s, SVMs and kernel techniques had a real high. So essentially back then, everything was support vector machines and kernels, and they were really the predominant machine learning algorithm back then. So nowadays it's neural networks. They were out of fashion back then, and this was really the high time of SVMs and kernels. So here are a few more resources and a nice lecture, very, very well explained, very well explaining support vector machines. This is a nice paper on SVMs, illustrating the background and also optimization algorithms. And in order to formulate the dual SVM, we discussed the Lagrangian and duality, and I really warmly recommend watching this lecture by Stephen Boyd. So this is a whole series of lectures on convex optimization, lecture 8, nicely explaining the concept of Lagrangian and duality. And if you have the bandwidth, really watch all these lectures. So Stephen Boyd is really great in explaining this to explain convex optimization and algorithms and theory. So like he's really great in explaining this, didactic genius essentially. So if you have the bandwidth, just watch all of these lectures. But in particular for this lecture, Lagrangian and duality, lecture 8 is relevant. So in today's lecture, we had, to summarize today's lecture, we discussed two of the strongest classifiers to date, random forests and kernelized SVMs. And random forests were essentially pretty simple. So they are a bagging technique, and bagging is bootstrapping and aggregating, which means so bagging means we train K classifiers on different bootstraps. And a bootstrap is really redrawing your data set with replacement. So very simple, and train a classifier on each of these bootstraps and then aggregate these results. So this is bagging, and random forests are really just bagging with randomized decision trees, and one of the strongest classifiers to date. And we discussed support vector machines as they are max margin hyperplane. We can formulate learning as convex optimization, and we had the primal and the dual SVM. And the dual especially allowed us to use this kernel trick, which, well, again, replace inner products with a kernel, and this yields implicit high-dimensional feature transformations and boosts of your machine learning algorithms. And this also concludes our second week, so module 2, dedicated to classification. So we discussed some background assumptions about classification, our assumption that our data stems from some true and unknown distribution, drawn IID, so independently and identically distributed. And we also discussed the Bayes optimal classifier, which we can get from the true distribution if we knew it, but well, we don't know it. We said in principle we want to evaluate and optimize the true error, which depends on the true distribution, and again we don't know that, and therefore we introduced train validation and test error, and this basic and this standard machine learning framework of splitting your data into train validation and test sets. We had the confusion matrix, and then we discussed these 5 classifiers: k nearest neighbors, naive Bayes, and decision trees, which are very basic and simple but work pretty well in practice. And today we discussed the random forests and SVMs, in particular with the kernel trick, which are some of the strongest classifiers nowadays. We spent some time on SVMs and kernel trick, but this really pays off, since this really provides a lot of insight on how machine learning works, or how machine learning methods are developed. And universities and companies really love to ask about support vector machines and kernels when they hire, since these are pretty deep topics and really separate newcomers to machine learning to more expert users. So in the next week, we will discuss regression methods, and then we'll continue with neural networks. Week 5 and 6 will be dedicated to unsupervised learning, and in week 7 we will talk more about evaluation and societal aspects.